Hello and welcome to lesson 19, uniform circular motion. Okay, so, um, whoop, I'm having a little trouble here. If we go back and think about acceleration in lesson 7, yeah, I think it was, we learned that acceleration results in a change in velocity. So, really, it's pretty straightforward. If you pushed something like we are, like in this picture down here, you are going to get a change in velocity, right? It's going to speed up. Seems pretty straightforward so far. Now, if we kind of change it a little bit, though, so look at this next picture down here, and we put the force on a bit of an angle, well, that's going to do something a little bit different. It's going to change its speed for sure, right? It's going to speed up a bit because you've got something that was traveling at a constant speed this way, and then you push on it from the side a little bit there. It's going to speed up, but it's also going to speed up in a different direction. It's going to change the direction that it went. That's kind of what we're going to be doing with our uniform circular motion. So it's kind of just to get you started there. So now, to get you ready for the concept in this lesson, we're going to have to stick pretty close to this definition. So acceleration is either a change in speed or direction. So something is technically accelerating if it speeds up or if it changes direction like we have up here. So if we kind of go down to this picture down here, so this is just a picture of a Ferris wheel, kind of, I guess. If you think about it, so you've got something on the top here, let's say, and it's going around in a circle. Well, at any point on this Ferris wheel, so up at the top, or let's say like right when it's right there, it's going down, and then right here it'd be going that way, and then here it would be going that way. Well, the speed at every point here, we'll say speed with just a V is speed, is going to be the same, right? It's going the same speed all the way around, but it's changing direction. You can see that this one has a different direction than this one, and this one, and this one. They're all different directions. So if we're looking at our definition of acceleration, then this thing is accelerating. There's a change in direction. So it's a little bit, we have to kind of think about acceleration a little bit different than you do typically. But this thing is accelerating. So which way is it accelerating? Well, let's go down to this picture. So we've got the same type of thing happening, right? So we've got a, well, picture this as being like a ball on a string. It's the same as the picture above, but let's just think like a ball on a string. It's a little easier to picture. Pretend that looks like a ball. Well, the ball wants to go this direction, right? But our string, which is represented by this arrow here, right, keeps pulling it down. So you can think about this ball. If you cut the string right here, well, this ball would travel in a straight line wherever it was. So if it was here, it would go straight down. If it was here, it would go straight that way. So it wants to keep traveling in a straight line, but the string keeps forcing it down. So it might be the first step to say, okay, well, the force of this thing must be always toward the center, right? You can see by the picture, it always is at 90-degree angle to what the speed is doing there, in this case, and in this case. So if the force is always toward the center, then really the acceleration is always toward the center too. Force and acceleration are pretty much the same things. Remember, force is equal to mass times acceleration. And that's it. So the only difference between force and acceleration is just mass. That's the only thing that separates them. So think about force and acceleration as almost being identical. Just mass is the only difference between them. So if your force is going toward the center, then your acceleration is always toward the center as well. So this is going to be a big concept on tests and quizzes and everything else. Which direction is the acceleration of a circle? you really need to know that it's towards the center. Yeah, that's gonna come up. So remember, however you need to do it, the acceleration in a circle is towards the center of the circle. Same with the force. And we have a name for our force. It's called centripetal force. So a lot of people have a bit of a misconception here, though. Let's say that you're on, like, I don't know, there's this like gravitron ride at the fair, where you get in there and it sucks you to the outside, and everybody's thinking, so centripetal force. Well, here, I'll draw that. This is our gravitron ride. Let's say that you're like on the wall right here, or any ride that goes in a circle. You really feel like you're being sucked out of the ride, right? It feels like you're going that way. So why do I keep talking about this force is going toward the center? It really feels like I'm being forced away from this thing. Well, it's not that mysterious, really, because and the way I'm going to think about it is, let's say that you're in a car. There's my awesome car. Here, I'll draw you. So you're driving the car, and you accelerate forward, right? Like, so you accelerate forward. The force is forward. What direction do you get sucked? Which direction do you feel like you're going? Well, you go backwards, right? You get sucked that way. So when the force of the thing is going one direction, you get pulled the other way. So it's the same thing with your ride. So when you're on the outside of your ride and it keeps feeling like you're getting sucked out of the ride, that's because the force is in the opposite direction. So it actually isn't that counterintuitive. It's the same thing, right? You always get pulled the opposite direction is what the force is. So yeah, so that might help you. Hopefully that kind of helps with clarify that misunderstanding. So anyway, the name of this force, this center-seeking force, the force that's pointed toward the center of the circle, is called the centripetal force. So that's centripetal means center-seeking in, like, I think Greek or something. Probably Greek. Okay. So one more thing before I move on that I want to point you to is just this. So if the centripetal force is removed, so i.e. the string is cut or you go flying off your ride up here or something, the ball will continue to move in a constant velocity in a direction tangent to the point where the force was removed. So that all sounds confusing, but it was just what I was saying here before. So if the ball was right here and you cut the string, then the ball is going to go in that direction. So that's just tangent to the circle, right? This is a line tangent to a circle. So yeah, that will also be something that will be on a test or a quiz, and it's going to show up a lot. So make sure you understand that concept as well. Okay, so this part, sources of centripetal force. Well, it's just really saying like the thing that's pulling it toward the center. I've talked about a couple already. This would be a string, right? So tension in the string would be the source of my centripetal force. So that's one source of a centripetal force. Force of friction. So again, you've got a circle. Something is causing this thing to go in a circle, right? If it wasn't, then it would travel in a straight line. So if this is a car, so if you got this is my car from above, well, friction must be the thing causing this to go into in a circle, right? So in this case, your centripetal force is your force of friction. They're all just different things that cause this thing to go in a circle. A different force pulling toward the middle. Okay, so it could be a friction force, usually with cars is kind of the example for that. And then another one that we're going to talk about a lot in another lesson, lesson 23, will be gravitational force. So again, you got a circle. Now we've got the moon, let's say, up here, and we've got the Earth here. Well, what's causing this thing to go in a circle? Well, it's the force of gravity, right? Force of gravity is pulling this thing toward the Earth. So that's my force of gravity. Well, that is also my centripetal force. That's the thing that's causing it to go in a circle. If it wasn't there, the moon would just go and shoot off in a straight line away from the Earth. So earlier I was saying that, well, you can think about which direction the acceleration is by knowing that, well, if the force is toward the center, then the acceleration is too, because they're so similar, right? Force is equal to mass times acceleration, almost the same thing. Well, and this is just another way of thinking about it, another bit of evidence here. So if you think about this example, so we've got VI, let's say at this point, goes off in that direction, and VF at this short time period afterward goes off in that direction. Well, they're only different, VI and VF, they're only different by their direction, right? They're exactly the same speed, they're just different direction. So if we look at this though, so if we go down here and think about it, okay, so change in my velocity here, so change in velocity, remember velocity means speed and direction. So if you just say change in my speed should be final velocity minus initial velocity. Well, you can subtract vectors, remember. So if we take this vector up here, right, so VI and VF, and we subtract the vectors, so if I start off with VF here, and then subtract VI, and the way you subtract a vector is just by flipping the arrow around. So this arrow was pointing in that direction, right? Now it's going to point this direction. We're going to flip it around. It's going that way, right? So that's just how you subtract those. And what you are left with is a change in velocity that is pointed straight down. So just another bit of math to kind of show that your change in velocity or acceleration is pointed toward the center. So however you want to think about it, you won't need to recreate this, but it's just kind of more proof that your acceleration is toward the center of your circle. Okay. So now that we have the concept of what's happening here, we've got these formulas. You're probably going to like these formulas, actually. They're pretty straightforward. A lot of just kind of plugging in the right numbers into the right formula. So if we have our centripetal force, then we can relate that to the mass times the speed of the object squared divided by the radius. Notice that this has to be speed, right? This isn't velocity, because our object is going in every which direction, right? It's going everywhere here. Like at this point, it's going that way. So we can only talk about the speed of this thing going around. We can't talk about the velocity because its velocity is constantly changing, right? Okay, so using our formula, well, if you want to just kind of look down at this one, you can just plug the numbers in, right? So it's asking calculate the centripetal force acting on a 2.5 kilogram object whirling at a speed of 3.5 meters per second in a horizontal circle of radius 0.8 meters. One little thing here, which is horizontal circle. We're going to be talking about vertical circles in the next lesson. So circles, in the vertical plane. So that's why it's saying horizontal right now. They're going to be easier, the horizontal ones. Okay, so yeah, just plugging it in and you end up with 38.3 newtons. Okay, and then down here, we're just talking about how to derive another formula. So if you want to look through this, I think you can look through it and figure it out for yourself, like how we come up with it. But we've also got this formula. So centripetal acceleration now is just v squared over r. And this one's also on your formula sheet. And I'm just going to skip this one. You guys can figure that one out for yourself. Okay. Another one, or another concept that's going to come up a lot, and in Physics 30 as well, is the idea of period and frequency. All right, so they're really two sides of the same coin, period and frequency. So listen carefully to the definition here. So period, it's going to have a symbol just t for time, right? It is just the amount of time required for one circular rotation. The unit for period is in seconds, because period is saying how long does this thing take to go around a circle. So how long did it take for this thing to go from there and then back to there again? That's it. That's all period is. Nothing too crazy. Okay, frequency isn't too bad either, but people just mix them up. Frequency is going to be the symbol f, like lowercase f. And actually it's kind of written like with a little twist on the bottom too. I'm terrible at it too, but that's frequency. Okay. And is the number of rotations or cycles in a particular unit of time. So period was how long does it take to go around a circle. Frequency is saying, okay, in 1 second, how many times does this thing go around? So I'll say that again. So in 1 second, how many times does something go around? So maybe in 1 second, this thing will spin around 5 times. That thing would have 5 rotations per second, or 5 cycles per second. And the unit for something like cycles per second is called hertz. One thing that might be more common to everybody is RPM. So maybe in your car you've kind of seen something was like, you're at like a certain number of RPM, you're revving too high, right? You're at a certain number of RPMs. So RPM is imperial. So it's what the Americans, or we still use in our cars too, but it's in revolutions per minute is what RPM stands for. So RPM is a unit of frequency. We just, when we're doing physics, like to talk in hertz instead. So instead of revolutions per minute, we talk in hertz, which is revolutions per second. That's the only difference. So that's all it is. So that's what frequency is. Now, getting back and forth between period and frequency is really easy. So let's say that they gave you frequency in the question, but you really were after period. Well, you can figure out what it is really easy by just going 1 over that thing. So if they give you frequency, period is just 1 over frequency. If they give you period and you want to find frequency, just 1 over period. That's it, period. You might be thinking I'm spending way too much time on this, but for some reason this concept really confuses people. If it's not confusing you, then great. Okay, so I'm going to move on. Okay, so the relationship between speed, period, and frequency can be readily understood by recognizing and distinguishing yada yada yada. So what this means, so if we think about, again, the circle, remember speed is equal to distance divided by time. Well, if we want to talk about this in terms of our circular motion, then think about d. Well, d would really just be the circumference of the circle, right? Like if you started here, it'd be like the distance all the way around from there to there, which is just your distance all the way around, your circumference. Well, circumference of a circle is 2 pi r. And your time to go from here all the way around, well, we just described period as that, right? The amount of time to go from like where you started and then back again, that's your period. So capital T. So that's just how we come up with this, right? Okay, moving on. And then another really useful one that you might want to use instead is going to be this one. I'll let you kind of look through and see if you can figure out how we derived that. But this is on your formula sheet too. So you've got a whole bunch of new ones on your formula sheet. Okay, so that's going to be it for this video. I'll carry on with the practice problems in the next video.